Chemists study matter, but energy affects matter. And so we study matter and how energy affects it. What is energy? Well, scientists define energy as anything that has the capacity to do work. And then we have to say, well, what is work? Work is a force acting over a distance. So if I take this bottle of acetone and I push it across the bench, I applied a force across a distance. I did work on the bottle of acetone. So work, energy is the capacity to do work. And then there's another concept of heat. Heat is a form of energy. It's the flow of energy from one thing to another that's caused by a difference in temperature. So we can have energy that is exchanged between objects through contact. Why do we put ice cubes in tap water? To make it cold, right? How does that happen? There's an exchange of energy. Heat flows from the warm tap water into the cold ice cubes. And as a result, the tap water becomes colder. We can also have energy from a collision being transferred. So think of energy as a quantity that an object or a group of objects can have. It's something that you can have. Heat and work are ways that energy is exchanged between objects. Heat and energy, those words, in my mind, get all tangled up, right? Energy is something you can have. Heat is a transfer or an exchange of energy. Energy can move into something or out of it. I think of energy as being a lot like money. You can have money. You can also transfer money from one person to another. And you can gain money and you can lose money. So I'll be using that analogy as we talk about energy. Of course, scientists classify everything, right? So we classify energy. There's kinetic energy. Kinetic refers to motion. So kinetic energy is the energy of motion. Here on this billiard table, we've got a ball rolling. It's in motion. It has energy. It has kinetic energy because it's moving. Thermal energy is energy associated with the temperature of something. Thermal energy is a form of kinetic energy. Kinetic energy is movement. How could something have thermal energy and be stationary? So my calculator is sitting on the desk. Is it moving? No. Does it have any thermal energy? Well, yeah, the temperature of the calculator is about 19.5 degrees Celsius, the same as in the room, right? It has a temperature that's non-zero. It must be at a temperature above that. It's got some thermal energy. So if thermal energy is a form of kinetic energy, what's moving in my calculator? The atoms and the molecules are moving. They're not moving relative to each other, or it would make a puddle on the floor. They're vibrating. Remember we said solids? Even solids are moving. The particles are moving. They're vibrating. They're wiggling, just like all of you guys are breathing at least, right? That is a form of kinetic energy. When you heat a substance up, the particles vibrate more. So thermal energy is a form of kinetic energy. Then there's potential energy. Potential energy is energy stored in an object or energy associated with the composition or position of the object. Here we have a disembodied hand holding a purple ball above the pool table. This ball has gravitational potential energy. If we let go of the ball, it's going to fall, right? The force of gravity is going to pull it down. Once you let go of it, that potential energy is transformed into kinetic energy as it moves. So energy can be transferred back and forth into different forms. Chemical energy is also a type of potential energy. It's not associated with something being lifted off the ground, though. It's associated with the relative positions of atoms, specifically the electrons and the nuclei, in the atoms and molecules that make it up. So chemical energy is a stored energy. Yes?
If the ball is on the ground, does it have potential energy?
If it's on the ground, I think technically it really doesn't have potential energy. The thing about energy, especially potential energy, is you have to define where is zero. Because if you dug a hole under the ball, it would still fall towards the center of the earth, right? Yeah.
Do most objects have chemical energy then?
Yeah, I would say most objects have chemical energy. Some have a lot more chemical energy than others. Things like gasoline, TNT, dynamite, those sorts of things have a lot of chemical energy. Things like water, not as much. So this is a summary. Energy is the capacity to do work. Two broad categories of energy, kinetic and potential. Kinetic has to do with motion, potential has to do with position or composition. Thermal energy is a subcategory of kinetic energy. It's the energy associated with temperature. That's the movement of the individual particles in the substance. And chemical energy has to do with the positions of the electrons in the nuclei. The electrons are negative, the nuclei are positive. There's a force of attraction there, and that's where the energy comes from. Other forms of energy, electrical energy. This is a type of kinetic energy. It's associated with the flow of electrical charge. So electric current is the flow of electrons through something. And if you've ever gotten a shock from a wall outlet, you know that there's a lot of energy there. Heat or thermal energy, we talked about that. That's associated with molecular motion. There's light energy, also called radiant energy. This is associated with energy transitions inside of an atom. There's nuclear energy. This is a potential energy found in the nucleus of atoms. And then chemical energy. This has to do with the structure of atoms, the attachment between the atoms, their positions relative to each other in a molecule, the molecule's positions relative to each other in the structure of the substance. We've talked about the law of conservation of matter. We need to talk about the law of conservation of energy. That states that energy can neither be created nor destroyed. When we have energy being transferred from one object to another, the total amount of energy when you start the transfer and the total amount of energy at the end has to be the same. You can't destroy energy. It's not truly lost, although we often talk about it being lost. It doesn't disappear. It doesn't cease to exist. It's just that maybe we can't find it anymore. So mechanical energy, she's pushing down this ball on the spring. So she's pushing down on this and she's putting mechanical energy into the spring. Then you release it, the spring unwinds and shoots the ball up, and it's transferred into kinetic energy. When we talk about energy being transferred from one thing to another, we have to very carefully define what we're talking about. And so we use the words system and surroundings. The system is the thing we're interested in. That's what we're studying. The system could be a molecule. It could be a beaker of liquid. It could be the liquid in the beaker. It could be all of the air in this room. It could be the building. It could be the planet. You can define the system any way you want. The surroundings is everything else. Technically the rest of the universe, but practically anything else that your system could exchange energy with. If you consider the whole universe every time, it gets a little tedious. So we're looking at the exchange of energy between the system, the thing we're interested in, and the surroundings. So what conservation of energy means is that the amount of energy that's gained or lost by the system has to be equal to the amount of energy gained or lost by the surroundings. So if we look at an energy gauge, right, before the energy transfer, our system energy is half full and our surroundings energy is only a quarter full, almost running on empty there. We're transferring energy from the system to the surroundings. Afterwards, the system has lost energy and the surrounding has gained an equal amount of energy. The surroundings gain an amount of energy exactly equal to what was lost by the system. And this is kind of, where I like to see energy as money. So it's like making a transaction. If I'm going to buy your calculator from you for $20, I give you a $20 bill, you take the $20 bill. Is there still $20? Yeah. It's just it was transferred from me to him. It's not like part of it left, right? Well, energy is something that is measurable, and so we need units. The amount of kinetic energy that an object has is directly proportional to its mass and velocity. And so we've seen this before. The kinetic energy is 1/2 the mass times the velocity squared. So units, the SI unit is the joule. I know it's spelled a little weird, but it's joule. The abbreviation is capital J. It's a relatively small unit. We can use metric prefixes with it. A kilojoule is 1,000 joules. So just to give you an idea, a regular light bulb would use 3.6 times 10 to the 5th joules in 1 hour. That seems like a really, really big number, right? But the joule is a very small unit of energy. That would be equivalent to 0.1 kilowatt hours. So the joule is defined as the amount of energy needed to move a 1 kilogram mass a distance of 1 meter. So pushing something that weighs a kilogram, 1 meter, that's how the joule is defined. And this gets back to the units we saw with that root mean square velocity equation, where we had R in terms of joules per mole Kelvin, and then we had kilograms in there, and things canceled out, and we magically ended up with meters per second. These are the relationships that get used in there. A joule is a Newton meter. A Newton is a kilogram meter per second squared. So you put them together, and a joule is equal to a kilogram meter squared per second squared. If that doesn't interest you, don't worry about it. A calorie is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. This is more interesting to chemists. So if you took 1 gram of water, say at 25 degrees Celsius, and you raised the temperature to 26 degrees Celsius, the amount of energy needed to do that is equal to 1 calorie. The relationship between calories and joules is given here. A calorie is 4.184 joules, so calorie is 4 times larger than a joule. This is an exact conversion. Pardon me? I would probably give it to you. You're going to use it quite a bit, and so you might end up just remembering it. But I'll give that to you. We are familiar with calories. People talk about counting calories and trying to lose weight and stuff. The calorie we're talking about is actually a nutritional calorie. It's calorie with a capital C. That can get confusing, capital C and lowercase c. A nutritional calorie is really a kilocalorie. So it's 1,000 calories. So a nutritional calorie is the amount of heat needed to raise the temperature of 1,000 grams of water by 1 degree Celsius. The amount of energy needed to heat up a liter of water. Here's some conversion factors. 1 calorie equals 4.184 joules. Kilocalorie is 1,000 calories, or 4,184 joules. And then here's the relationship between joules and kilowatt hours. I'll give you the calorie to joule conversion. If there's kilos in, kilocalories, kilojoules involved, you should be able to do that. It's the same as going grams to kilograms. And then this is just kind of interesting amount of energy to light a 100-watt light bulb for an hour, amount used by your body running a mile, and all of these, of course, are approximate. Amount used by the average U.S. citizen in one day. It's kind of interesting in the different units.